Today we're looking at section 11.1 on basic concepts. These are basic concepts of probability. In chapter 11 we will be applying many of the ideas we learned back in chapter 10 when we talked about counting. And we begin with the definition. An experiment is any observation or measurement of a random phenomenon. For example, you may look at a class of students and you may be measuring their heights. That would be a measurement. Or you may observe that some students are males and other students are females. So you may record the number of each gender. So these would be examples of experiments. A sample space is a set of all possible outcomes. So if you're talking, for example, about the gender case, the set of all possible outcomes would include female and male. Those would be the all possible outcomes. Now, a theoretical probability, we have a formula for that. And this is sometimes called classical probability formula. This is what we expect to happen. Okay, it's based on the mathematical principle, what we expect to happen. And it says if all outcomes in a sample space are equally likely, and E is an event within that sample space, then the probability of E is equal to the number of elements that are successful, that is the number of E divided by the number in the sample space. So if we were talking about the probability of selecting a female, and let's say that we have a class of 30 students, and we have 10 male, and we have 20 female. Okay, so we have a total of 30. Okay, the probability of a female student would be, if we randomly select a student, would be 20 out of the total number. That's the number in the sample space, or 2/3 if we reduce it. Okay, so it's the number of events that are successful over the total number in the sample space. So if we look at example 1, consider the experiment that consists of tossing a coin once. The sample space gives us two outcomes, heads and tails. Probability of heads, we have two possible outcomes, so that's the denominator. And there's only one head, so 1 out of 2. Probability of tails. We again have two possible outcomes, and the probability of getting tails, there's only 1 out of the 2. Back in this case, when we looked at the females, we had 20 out of the 30. So we had a little bit different situation. Now consider the experiment that consists of rolling a single die once. What would the sample space be? What would the sample space be? So let's think about it. If we have a normal die, which is singular for dice, we can roll a 1, a 2, a 3, a 4, a 5, or a 6. So we have 6 possible outcomes. What is the probability of rolling a 2? And notice we're using this notation, probability of. Done it several times here. So what's the probability of rolling a 2? Well, if we roll a die one time, we have 1, 2 as we look at our sample space out of 6 possibilities. So the probability would be 1/6. What's the probability of rolling a 5? Again, we have 1 5 out of the 6 possibilities. Finally, what is the probability of rolling a 7? Well, we see we have no 7s So an impossible event has a probability of 0. When the event is impossible, the probability is equal to 0. All right, so this is the classical or the theoretical probability. All right, an empirical probability. If event E is an event that may happen when an experiment is performed, then the probability of E equals the number of times E occurred divided by the number of times the experiment was performed. So suppose that a coin is flipped 100 times and that 46 heads, and this should be 54, I have a typo, 54 tails are recorded. Then the empirical probability of heads would be 46 out of 100, or 0.46. Probability of tails, on the other hand, because we had 54 tails out of the 100 tosses, would be 0.54. Notice that when we conduct an experiment, it's slightly different. We may get a slightly different result from what we expect to happen in the theoretical probability. So the theoretical probability is what we expect to happen based on the mathematical model. In the case of an experiment, the empirical probability is what actually happens. So we might get 50 out of 100, but in this particular case, we ended up with 46 heads and 54 tails. Now, the law of large numbers says as we repeat an experiment more and more times, the proportion of outcomes favorable to the event will tend to get closer and closer to the theoretical probability. So if instead of 100 tosses, we set up a computer simulation to do 100,000 tosses, then there would be a probability would get closer and closer to the 0.5 we would expect. Now, odds are slightly different from probabilities. They're related, but they're not exactly the same. Odds in favor is where we compare the favorable outcomes to the number of unfavorable outcomes. And the odds against is where we compare unfavorable to favorable. So I usually, because we use the colon sometimes, and textbooks have all kinds of ways to explain this and use all kinds of fancy formulas. I find the easiest way to do it is think exactly the way I've written these: favorable to unfavorable and unfavorable to favorable. So let's look at a couple of examples. What are the odds in favor of rolling a 2? What are the odds against rolling a 2? And so, what are the odds in favor of rolling an even number? So I have 3 questions here, so let's start with the first one. On the die there is 1 favorable outcome, that's the 2, and 5 unfavorable outcomes. So the odds in favor of rolling a 2 will be 1 to 5. And let me get my highlighter. And you can say it with words or you can use the colon. Notice the colon is not used when we're talking about a probability. This is only for odds. You can talk about using a fraction when you're talking about odds. I tend to stick to the colon or the word 2 simply to designate the two are slightly different. They are related, but they are slightly different. So that means the odds against rolling a 2 will be the reverse. It's going to be 5 to 1 or 5 to 1 using a colon. Okay, now let's talk about the odds in favor of rolling an even number. We have 2, 4, and 6. So we have 3 even numbers. 2, 1, 3, 5. 3 odd numbers. So 3 to 3, or we reduce that. We treat it like a fraction, 1 to 1, or using the colon, we can do 1 to 1. Okay, so those are odds. They are related, but they're not exactly the same. Okay, so let's take a look. A glass bowl contains 10 red M&Ms, 5 blue ones, 15 brown ones, 8 orange ones, 7 green ones, and 5 yellow ones. What are the odds in favor of drawing a red M&M if one is selected at random from the bowl? Okay, so let me get my pen back here. All right, so we have 10 red ones, and we need to add up the others. 20, 35, is it 40? Okay, we have 10. We have 20 if I add the blue and the brown, 15, 20 if I add the green and the yellow, so we do have 50 in all. So we have 10 that are red to 40 that are not red. All right, what are the odds? And notice we can reduce this to 1 to 4. That would be the final answer. What are the odds against drawing a red one? That would be reversing it, 4 to 1. What are the odds in favor of drawing a green one? Let's see, how many green ones do we have? Oops, I was trying to highlight. All right, so we have 7 green ones, so it's 7 to 43. That would not be green. So 7 to 43.